more or less back to operation.
I see.
But it is the middle of the summer, so. So no, but I would say it's quite many people are, especially because we have popcorns, you know.
So Harold, can you test your screen sharing just to see that it works?
Sure.
Okay.
All good?
Yeah, perfect. So now just close that so that I can, okay, great. And then
Sure.
I'll share my own screen. Okay. And actually, it is time, so we will be starting. So I showed the poster of the school. It's the final session this afternoon Europe time and this morning US time. And it's been a very unusual kind of event, of school, I should say. It would have been live, and that would have been far more pleasant. But I think that all told, despite the fact that we had to adopt this online format, I sincerely hope that everybody enjoyed it. And so what would be very helpful would be if all of you were to send us a little feedback on how you perceive this Les Houches meeting, and then without further ado, what I'll do is introduce our last speaker of Les Houches. So I will stop sharing my screen. Okay, and admit, and then I will introduce Harold very briefly. So Harold Hwang is a professor at Stanford. So he got his PhD in physics from Princeton University in 1997. Hwang was his supervisor. And during that time, he was also a research assistant at AT&T Bell Labs for 2 years. And after his PhD, he returned to Bell Labs. And from 1996 until 2003, he was member of technical staff. I don't quite understand the name, but anyway, in the Department of Materials Physics Research. And during that time, he conducted the research, which is actually the theme of this school. So that was quite an event. After that, Harold became an associate professor, then professor in the Department of Advanced Materials and Department of Applied Physics in Kashiwa. And then from 2010 until 2014, he became team leader of Correlated Electron Research Group in RIKEN. He was appointed at Stanford from 2010 on, and so now he's a professor in the Department of Applied Physics and Department of Photon Science at SLAC. He's also deputy director of CMIS, the Stanford Institute for Materials and Energy Sciences. Harold has been awarded quite a number of prizes, and I won't list them all, but just name a few. So in 2008, the IBM Japan Science Prize. In 2013, the Hwang Prize in Science. And in 2014, the Europhysics Prize, along with Jean-Marc Triscone, who is here, and Jochen Manhat. He is also a fellow of the American Physical Society. So this being said, I will give Harold the go-ahead, the green light. So please begin your presentation, your lecture. So
Okay,
it will be an hour and a half, and
Mhm.
people have questions. Please use the chat feature to ask, and at the end we'll ask questions, unless it's pressing. Then you unmute your mic and ask the question directly to Harold. Okay.
Yeah, first of all, thank you, Mark, for the kind introduction. And I wanted to thank you and your co-organizers, essentially for organizing not one, but two meetings. So that must have been an incredible amount of work, but thank you. So I'm a bit sad because my whole family and I were looking forward to a nice time there in Les Houches, but you know, c'est la vie, right? I'm glad to have this opportunity, and I will leave it to Mark to some degree, but if we're a small enough group, then I have no problem if you guys want to come in with questions as we go. But either way is fine. So look, I thought I would tell you a little bit about work we've been doing as a first stab of organizing our thoughts on what it means to see superconductivity in the infinite layer nickelates. This has been an activity that has been quite exciting. I thought also, I think there will be materials distributed or this recorded. So let me both acknowledge and give you some references in case there are aspects of particular interest to you. I'm going to highlight, not everyone. You can see we bothered quite a few people and collaborated with them on this work. But to emphasize the young people I've had the pleasure to collaborate with, these four gentlemen in my own group, Denver Lee, actually a graduate of Jean-Marc Triscon's group, by the way, in Geneva, Kyuho, Bai, and Motoki have really done an outstanding job on some of the most difficult materials I've ever encountered to work with. And we've also worked closely with the group of Lena Kukurtis at Cornell, and in particular, an outstanding graduate student, Barrett Gudge there. So yeah, I won't list all the names, but I should say that immediately we've benefited from quite a few interactions and insights from expertise all across the scope related to this field. I would say I wanted to thank, for example, X-ray scattering and Rick's type of measurements led by Matthias Hepting, who's now at Max Planck Stuttgart, and Wei-Sheng Li. Theoretical engagement with Tom Devereaux and his group members, Jan Zanen, George Zawatsky, Sri Raghu, a colleague at Stanford, and Ronnie Tamali, and so on. So also, I should say that I won't show much of it, but for some of the X-ray scattering, we were running around trying to get beam time everywhere. So many thanks to various beam lines around the world for access for these experiments. So let me just tell you the story, basically, of this work. And it is part of a long-standing notion, right, that far predates us, which is to look for new superconductors, and in particular, after the quite surprising discovery of superconductivity in the cuprates at IBM Roussillon, what is this now, 34 years ago, quite a long time ago. There have been for decades discussions of whether some of the features or the electronic structure could be mimicked in other compounds. So I think many of you must have heard about cuprates to some degree, but let me just survey for generality a few key points that would be relevant, at least for our thinking. One is, it's actually quite a complicated phase diagram, but simply speaking, the cuprate superconductors all arise from a parent compound, which is an antiferromagnetic insulator, so-called mod insulator, in the sense that the insulating gap comes around from strong electronic correlations. And as you actually either hole dope, as shown here, or electron dope the system, you encounter a dome of superconductivity. Now, there are quite a few other instabilities and important features that I'll kind of neglect in this discussion, but this statement is quite general, that we're always doping out of this antiferromagnetic insulator. The second thing that I will emphasize here is that the crystal structures, there are many, many of them now, have different stacking motifs, but the common ingredient is a quasi 2D crystal structure composed of copper oxide planes and various stacking sequences with rarer spacers and so on. So it's well understood that the relevant electronic states near the chemical potential are hosted in the copper oxide planes. And in particular, one of the important notions for hole doping in the system is the so-called Zhang-Rice singlet. I'll come back to this point later in the discussion, but namely that if I think about an isolated hole in the system, you can think of this as a system where the hole is actually coming out of the oxygen ligand field and making an overall singlet, and this is kind of an essential constituent entity in thinking about superconductivity and normal state transport in the cuprates. And it nicely ties together this notion of having strong antiferromagnetic interactions between copper sites and how hole doping may give rise to superconductivity. So this is from a review article a few years ago, so-called Gang of 5 paper that is well known, I think, to you. So the basic question is rather simple, which is, can you make a nickelate structure look like the cuprate superconductors? Okay. In particular, you can see, for example, that nickel is 1 over on the periodic table. So specifically, if you can make something like a rare earth 3+ nickel 1+ O2, this should be isostructural and isoelectronic to the so-called infinite layer cuprates, say calcium or strontium copper oxide. Okay. Indeed, this, as I said, I believe this idea was kicking around even before this, but the first 2 papers that I'm aware of where people explicitly thought about this analogy was from this work in 1999, Nisimov, Morris Rice, and others. What is this, 5 years later by the group of Warren Pickett at UC Davis. So these are both electronic structure calculations, but they were basically starting to think about this process. And you can see the interest, right? Possible nickelate analogs to the cuprates, but in Warren's paper emphasizing that actually there are key differences between nickel 1+ and copper 2+. So I'll come back to this point later, but if we take the LDA, so the uncorrelated band structure limit of these compounds, there's pretty good convergence nowadays. But the electronic structure looks something like this. These big, large, hole-like pockets are very reminiscent of the dx² - y² hole pocket in the cuprates. But in addition, there are 2 electron pockets, small ones, here in the corner, and one you can't see in the zone center, that have a few % of the electron density hosted in them. So that is one of the aspects that this paper is emphasizing. Now, from a materials point of view or a chemistry point of view, you can immediately see that while this analogy would hold in the sense that you would have 9d electrons in the system, is quite peculiar. Nickel 1+ is an extremely low oxidation state, and that is, in some senses, much of the thing that we've been focusing on and struggling with, to be honest. So that's a very unusual oxidation state. So let's talk about how this can be accessed. So as you may know, the most common oxidation state for nickel is nickel 2+, so nickel oxide, this famous mod insulating compound. A secondary valence is nickel 3+, right? And so starting in early 80s, very clever chemistry efforts discovered that you could do something that they termed a topotactic reduction reaction. And what that means is they started with lanthanum nickel O3, a perovskite version of this compound. And then they could deintercalate rows of oxygen to make the so-called Brown-Millerite structure. So here's the formal chemical formula. And if you go even further, this, by the way, would correspond to nickel 2+. And if we take the other row out, you get indeed this direct analog to the infinite layer cuprates and a formal valence of nickel 1+. So these are generally understood to be metastable compounds. There's no known way to access them in some sort of thermodynamic synthetic technique. And so rather you're using the scaffolding of the kind of perovskite precursor phase in order to kind of stabilize this cascade of reduction reactions and maintain the crystal structure. This was first discovered in 1983 using hydrogen gas as a reducing agent. There was quite a lot of struggle in a small but active community because it was very difficult to reproduce. There were lots of controversies actually about the reality of this of these phases. And the next key step was from this paper, a group at the University of Liverpool, that showed that you could actually quite reproducibly and stably observe these transitions using metal hydrides like calcium hydride as your reducing agent. And the other key step that I should acknowledge is about a decade after this work from Liverpool was the discovery or the finding at the University of Kyoto University that you could actually undergo these sequence of reactions also in thin film form, which is the approach we'll be taking. So just to give a broad picture to those kind of further abreast in the field, what we're trying to do is marry essentially oxide heterostructures and thin film efforts that we and others in the community have been pursuing with these soft chemistry techniques. And so just mostly just for something visually nice to say that many of the people, the organizers, this community has gone a very, very long way to take very complicated structures. These are perovskite titanates in this picture here, and really start to push the atomic limits of being able to make heterostructures and interfaces with atomic precision. Okay, so this is something that we've been doing for a while that we'll take advantage of. The second thing that's amusing is the very key step for this looks something like this. Sometimes it's easier or nicer to show how it looks like. This is how we're doing this oxygen deintercalation reaction. So what you're seeing here is 2.5 by 5 millimeter substrate with a thin nickelate film on top. Our current approach is to loosely wrap this in aluminum foil, mostly just for cleanliness or physical separation. These pebbles down here are calcium hydride, so something like 100 milligrams of that in an evacuated glass tube. And we're annealing this at a few hundred, to 250 degrees C or so for a few hours. So despite the rather expensive and fancy UHV equipment that I showed you in the previous slide, this is a key step. It's very modest looking, but trying to sort this out, frankly, from our end, mostly empirically, was one of the key aspects of this work. So as I had showed you before, that we were certainly not the first to invent any of these techniques or the thin film implementation, but we were rather interested in trying to go now towards dope versions of this with this analogy to cuprates in mind. And the basic reproduction of the synthesis worked well, but we could never dope them. So I thought I would tell here and there stories about how serendipity is such a key factor in all of this. A postdoc that worked with us, Hwang, actually spent a number of years, a good fraction of her effort over a number of years as a postdoc in our group, was able to synthesize these parent compounds, but doping was never quite successful in the approaches we took at that time. Not to say that this is not possible, but certainly in our efforts using ionic liquid gating or trying to fine tune the oxygen stoichiometry in these reduction reactions, were basically unsuccessful. I should say that she's doing well in science and she's back in Tsinghua and doing well, but certainly this was a tough time for her and for us. But nevertheless, there was very little, especially spectroscopic studies of these compounds, and it was still certainly interesting to ask what's going on. And so with her samples, we started to collaborate with Wei Sheng, looking at XAS and RICS and so forth. So a lucky accident was just as she was leaving and Denver first arrived, or just after that point. As usual, we needed a few more samples, and Denver kindly jumped in to make them, but also then, of course, got interested in asking, you know, what were the issues and can we think about different approaches to doping? So yeah, so then with that kind of fragile link, we continued this work, and the idea for doping was perhaps rather than trying to dope the infinite layer compound after synthesis, why don't we chemically dope the perovskite phase and then reduce it to the infinite layer phase? And it's funny that Mark gave an extensive introduction. And so indeed, at one point, I was a summer intern at that time, AT&T Bell Labs. And one of the last things I was working on before going to grad school was doping, actually, trying to do electron and hole doping of these perovskite nickelates. Now, many of you in the audience, or Jean-Marc's group certainly have expertise in studying the system. It's a very fascinating system in itself, also in the perovskite phase. What you can see here for, in this case, neodymium nickel 03, it has a dramatic first order metal insulator transition. It's one of these very lovely canonical systems that exhibits low temperature, magnetic, orbital, and correlated ordering phenomenon. And you can see here that we tried to do different types of substitutional doping. And it's kind of ridiculous in retrospect. This is very close to what we need for our work now. And this was 1994, if my eyes can see properly. So quite a long time ago. So that was the idea. And Denver tried lots of things, actually, initially in the lanthanum strontium version of the system. And you can see here, I should say this was preliminary work. It's probably worth revisiting in that we know much more now about the synthesis of the system than we did back then. But what you can see from his resistivity as a function of temperature traces, that actually it's not so systematic per se, but with doping, and especially with about 20% doping, we have a minimum in resistivity, okay? So this starts to seem interesting. It's on the verge, qualitatively, of looking metallic. And I like to quote, actually, a mentor at that time when I was at Bell Labs who told me, this is Hida Takagi, who was a visiting scientist at the time. And he said, you know, for layered oxides, when you get on the scale of about a milliohm centimeter, you know, this starts to be right at the threshold where you can induce kind of coherent states, and interesting things happen: superconductivity, charge density wave phenomena, and so forth. And so the idea was simply to say, okay, so lanthanum looks close. Why don't we go to a smaller ionic radius in neodymium, and perhaps that should increase the electronic bandwidth in the system. But also, to be fair to history, I had also said to Denver, hey, you know, we've already spent so much time unproductively in this project, let's give up. And of course, another important good fortune here is that he ignored me, as should have been the case. And in fact, here I show you directly a trace of his first partially superconducting sample. Like most things, that only seems to occur in the middle of the night. And you can see here, this resistivity scale is not 0. So it's only a partial transition down to 2 Kelvin where we measured. But this was the first step in seeing something interesting. I should say that we didn't submit this first paper until about 8 months later, and you can ask, you know, what took so long? And it was an extremely difficult materials challenge, and it's a rather interesting one. So let me tell you just in a few words what is the issue. As I said, that the nickelates most stably want to be nickel 2+. Nickel 3+ is a secondary oxidation state. And from a chemistry point of view, what we're trying to do is rather extreme. And namely, we're trying to stabilize a very unusually high oxidation state, so formally something like nickel 3.2+, which is already very hard. In bulk, would require high pressure oxygen, for example. And then we want to reduce it to a very unusually low oxidation state, And we want to use epitaxial stabilization in thin film form, as discovered by Professor Shimakawa's group. And all the while, the in-plane lattice parameters are changing by about 3%. Okay, so it's kind of a mess, but quite an interesting challenge, actually. And so let me give you a picture of the kind of sample probably we're looking at in this partial transition. It looks terrible, and that's the point in some sense. There's all sorts of decomposition phases, secondary phases, and you can hardly see it here, but just a sliver at the interface turns out to be this infinite layer structure. So with considerable effort, Denver could then get this to the point where uniformly in the first few nanometers at the interface, we could indeed stabilize this infinite layer structure. You can see this in the Fourier transform. This tetragonal distortion is corresponding to this planar contraction. But still, the vast majority of the film volume, if you will, is some rather messy unknown structure. Now, what the Kyoto people first showed us, and we're also seeing here, is that doing this in thin films has a particular advantage, namely that we're using strontium titanate here, but typical perovskite substrates are stable against this reduction reaction that we're using to transform the nickelate. And therefore, not only does it provide a template, allows you to do something you can't so far do in bulk powder samples, namely you can orient a single crystal thin film, or at least in this case, just in the vicinity of the interface, you can stabilize this structure. So that's actually quite important and powerful for our work. I should also say that this was already discussed somewhat in the prior literature. So this is, for example, lanthanum nickel O2 thin films. This is neodymium nickel O2 thin films. There are many interesting details, but the point I emphasize here is the same thing that I just described to you, that in the vicinity of the substrate, you have this epitaxial stabilization of the infinite layer phase. Above that, you have various secondary or competing phases or decomposition products. For the neodymium nickelate, the same thing is observed. Okay. So the final step to get to something reasonably stable in the majority of the type of structure that we look at to this day is to take that idea and just double up. Namely, why don't we take advantage of the things we know as a community in making perovskite heterostructures and grow a strontium titanate cap so that we have this proximity stabilization in both directions, okay? And so indeed, this is what we found. This is earlier work, but you can see here of order 9-10 nanometer thick sample looks reasonably crystalline coherent in this infinite layer structure. I should say that, by the way, the previous terrible looking TEMs were not Lena or Barrett's doing, the Cornell collaborators, but from here on out, including this one, this is their work. So yeah, that is also currently the limitations of what we have in terms of a typical maximum thickness of sample. So it is rather restrictive, unfortunately, that we're limited to this 10 nanometer scale. And going back to this prior work, you can easily imagine that basically there is some length scale of a few nanometers from the interface where we can have this kind of proximate stabilization. And so you can roughly double that, but going beyond that, what will happen is these sorts of secondary phases will appear kind of in the midst of the film. Okay. So this gets us to basically a reproducibly complete transition. Still at this stage, bouncing around quite a bit. So I won't go into the details, but basically now we can get real zeros of the resistance, quite a bit of scatter for films that were nominally grown and reduced in the same conditions. We've made some progress on this, as I'll show you as we go along. And so as of kind of a year ago, this is where we stood, and Denver's first paper on this topic. So let me just walk you through briefly the status at that time. So this is just a nice illustration of this calcium hydride reduction reaction. this epitaxial relationship between the infinite layer structure and the substrate. And you can nicely see this by X-ray diffraction, right? You can see, for example, the perovskite peaks shifting out to higher 2 theta values corresponding to the reduction of the C-axis lattice parameter. And in all of the things I'm going to discuss here, the in-plane lattice parameters, excuse me, that can be observed by reciprocal space mapping are locked into the substrate. Okay, so we're always in a regime where the substrate dictates the in-plane lattice parameters. So now if we look at the perovskite version of this thin films, here's neodymium nickelate. Again, it shows this characteristic large first order phase transition between a metal and an insulator. And I remind you, this is a 7D electron configuration. And again, as a kind of, I had been fooling around with as a summer student so many years ago, if we dope, in this case, nominally hole doping, we suppress this metal insulator transition. Now, if we reduce these compounds into the infinite layer form, so nickel O2, the undoped case, you can see here in red, has a weak insulating upturn. Of course, there are still many open questions about this, but I should emphasize that this is not a good insulator. This is definitely not what you would see for the undoped cuprates, where the transport gap would be much, much larger. As far as the dope case, what you see is indeed a nice superconducting transition. And again, the characteristic scale for, let's say, the room temperature resistivity that's relevant here is about 1 milliohm centimeter. I'll make a few comments more on that as we go on. So looking at the basic superconducting properties, even though this is quite rather unusual and difficult to stabilize phase, even our first experiment showed that it was fairly robust, namely that the critical current densities were approaching 200 kiloamps per centimeter squared. Now we, in some cases, can get up to 350 or so. So this is a non-trivial fraction of what you would see in, say, cuprates. And so quite a robust critical current. If we look at the magnetoresistance, this is for the perpendicular magnetic field orientation, you can nicely see the suppression of TC, and you can extrapolate out a Ginzburg-Landau superconducting coherence length of about 3 or 4 nanometers sample to sample. And finally, by doing a two-coil measurement, we looked at the mutual inductance. And what you can see here is that the onset of superconductivity, global superconductivity, then you can see the screening response of the sample between the two coils. And we're probably still at a very cautious stage of trying to give you hard numbers. But let's just say with the variations available for order parameter symmetry or the scale of relevant disorder, whatever else is true, the London penetration depth will be on the scale of a micron or so. So it's a very kind of extreme type 2 superconductor. So there are, of course, a million questions that come up, and I tried to frame a few of the ones that are in a lot of people's thinking. And of course, the motivating question was, to what extent is the D9 configuration hosted by nickel the same as that hosted by copper? And again, there are two things to emphasize: the fact that we are doping out of this antiferromagnetic insulator in the cuprate case. This has been long suspected to be a key ingredient in terms of, let's say, lots of thoughts about spin fluctuations of this competing order phase mediating superconductivity and what have you. The other thing that I'll come back to towards the end is that the crystal structure, again, is defined by copper oxide planes separated by so-called charge reservoir layers. This is where people, for example, do substitutional doping, and that charge is transferred, let's say, to the relevant CuO2 plates. So on the other hand, even though the structure and the electron configuration is the same, there are fundamental distinctions from the cuprates. One of them is actually back to these Liverpool studies, namely that they did powder neutron diffraction refinements, and they found no evidence for magnetic order down to about 5 or 2 Kelvin or so. So that obviously is a key distinction between, as compared to the cuprates. There, I should say, there was a recent paper on CONMAT from John Mitchell and collaborators at Argonne in powder samples as well. Again, they see no evidence for magnetic ordering. The other key distinction is that we have a very different orbital energy level alignment. Okay, and that really just has to do with the fact that we are 1 over on the periodic table, and we're at a lower oxidation state. And so despite these similarities, there's a very big distinction in where things line up. So if I give you this cartoon of the cuprates, the schematic electronic structure is that you have strong correlations that give you a lower and upper Hubbard band, right? So this on-site Coulomb interaction, this U that people talk about, splits this on the several electron volt scale. The oxygen 2p band is lying around here, such that when you start to whole dope this system, you start to form states of this Hwang singlet character here. Namely, it's composed of the hybridization between the copper 3d x squared minus y squared and the oxygen 2p states. The notion is in this Zawadzki-Allen-Zonin scheme that you're in this charge transfer regime. And so the hole is actually coming out of the oxygen ligand field, and it's making an overall singlet in the sense that these are now anti-aligned. Okay. So how about the case for the nickelates? The nickelates, again, by virtue of where we are electronically, has kind of similar overall landscape. But the caveat is that when we start to dope the system or play with the system, we're living very, very far up compared to the edge of the oxygen 2p band. Namely, we're looking at a manifold of states composed of hybridization between the upper Hubbard band of the nickel 3d states and actually the 5d electrons of the lanthanum, neodymium. The details don't really matter here, with a broader bandwidth across here. Okay. And so early on, this led people, various people in my own discussions. Jan Zonen was the first to point this out. He was on sabbatica last year at Stanford, saying this is rather interesting in that it might be an oxidic analogy to a Kondo system, meaning rather than a narrow 4F band in the midst of other things, here we have this rather narrow upper Hubbard band in the midst of these 5D states. But whatever else is true, what we also can say is that if we are thinking about doping in this system, let's say a little bit of whole doping in the system, we're really then talking about states derived from these nickel 3D and in this case lanthanum 5D states. And so how they look like from this paper here, what you can see is that indeed the nickel states look very much like the Hwang singlet, but with much smaller amplitude, as we'll find in a moment, right? That even though we're several electron volts above, there's still quantum mechanical hybridization. We have states like this in terms of a real space kind of Wannier picture. But again, we have what's very different from the cuprates, this hybridization with the rare states. And so something that has a much more three-dimensional character. Okay. So how can we see this? Sorry, this is a bit of a busy view graph. Let me just talk through a few of the key points. Let's first just simply look at the XAS spectra of the oxygen K edge. What you can see here is for nickel oxide, so the D8 configuration nickel, you see this strong pre-peak feature, right? And similarly for lanthanum nickel 03. This is well documented in the prior studies in the literature. But when we go to the infinite layer version of this series, you see almost no pre-peak amplitude, okay? And so this, we think, is a measure of this x squared minus y squared state. So it is there, but it's very small amplitude, and that is very different from, again, the cuprates or the other oxidation states of nickelates, okay? And the same can be said for the neodymium version. So this was a study just of the parent compounds. And so similarly, you could kind of go through the spectroscopy of looking at the occupied and unoccupied states to orient yourself in the world. So again, nickel oxide, the perovskite nickelate, and the infinite layer nickelate. And the bottom line summary, let me just stick to these cartoons here, is that we have a rather unusual regime that, despite being very much on the right-hand side of the periodic table, that we believe that we're in something that to some degree is rather akin to the Mott-Hubbard insulating structure rather than a deep charge transfer insulator as found in the cuprates. Okay. So let me, how am I doing for time? Hopefully okay. Go through the doping dependence of the system. So all of the things I told you about was just looking at 20% doping. And of course, the immediate question is we know that the parent compound is non-superconducting. This looks like it might be a dome structure, and indeed that's what we find. Is quite a bit of work because of all of the materials difficulties. Let me try to give you a representative picture of a doping series. This is a beautiful and difficult work Barrett had done. And this is trying to be kind of fairly representative, meaning there are stretches of these films that are nicely coherent, but there's a fairly high density of defects, extended defects. So you can see this box here, for example. So if you're interested in these details, we've described them in some detail in this paper by Kyuho. But let me simply say that the structures we're finding are likely to be of the variant of having anti-phase boundaries, as well as, in particular, Ruddleston-Popper-like layered intergrowths. Okay. What this means then is for bulk volume sensitive measurements, like TC or the lattice constants, or the static Hall field, as I'll show you. These are quite quantitatively reproducible. But as far as the magnitude of the resistivity, there's a fair amount of jitter sample to sample. And we believe that's coming from the details of the density and distribution of these sorts of extended defects, but we'll go into now in a moment. So first, in terms of the doping dependence, let's first look at the crystal structure. So what you see here is the C-axis lattice parameter monotonically varies across this doping series. Again, I remind you that in all cases that the in-place lattice parameters are clamped to the substrate. So this is in some sense an artificial geometry imposed by that strain. Right? It's actually kind of strange, right? Because the dope version, there is no, or there is now, but coming out, but there was no prior bulk work. So it's a little bit of a constrained case that I show you here. I will contrast that our doping studies with kind of the canonical 214 cuprate system, work of Hida Takagi. And you can see that qualitatively there are similarities in terms of having an expanded C-axis lattice parameter. I should say, though, that the sensitivity is much, much higher, meaning this variation is about a factor of 5 or more larger. This has been seen in electronic structure calculations as a function of rare earth site. In this case, at the simple-minded way, you could say is that the strontium ionic radius is rather larger than the neodymium, so there will be an expansion you would expect. And of course, then there might be competing electronic degrees of freedom, but in any case, this is within our expectations. And in terms of the resistivity as a function of temperature, I'm going to show you here first what I'll call representative samples. So here's the undoped neodymium nickelate. It has this low temperature upturn. Okay. And as we start to dope strontium into the neodymium site, you can see that it comes down. We have a range of superconducting samples. And then if we want to use this language for overdoping, we return back to this insulating upturn. Now, as I said, there are some variation sample to sample. So this kind of figure should be taken with some care, if you will. We've tried to show you representative variations here. These are nominally identical samples, different synthesis runs, but all other things being equal, what you can generally see is that in most cases, the temperature dependence is qualitatively similar, but in detail, there can be significant variations up to like a factor of 2 in terms of the magnitude of the resistivity and so forth. But what's already strange, especially compared to the cuprates, is that the entire variation of the resistivity is rather narrow. It's within an order of magnitude or so. Right? And this is in strong contrast to the cuprates, where we have, you know, a good insulator for the parent compound, and what's known to be a pretty good, hopefully simple Fermi liquid metal for the highly overdoped non-superconducting samples. We have something rather peculiar with respect to those end members. So to show this in phase diagram form, here's the nickelate phase diagram we deduce. These zeros are statements that, at least down to the base temperature of our dill fridge, we see no signs of the onset or the proximity of superconductivity, and we see a narrow dome, okay, in this range. And just to give you a point of comparison, this is what you see in the 214 cuprates for whole doping. Okay. So tantalizingly similar in approximate position and qualitatively. It's quite a bit narrower. It's actually more similar to what you find in the electron doped 214 cuprates. But the thing I want to emphasize again here is this rather strange normal state on either side of the dome. In both cases, we have this rather weakly insulating upturn. Okay? And one way I can try to show you or at least some of our thoughts on this, is to give you a low temperature normal state slice of the resistivity. Now, this is for all of the samples, or for several samples at each doping. So you can see the scatter, which is non-trivial. And yet the overall trend, I hope, is also very convincingly clear, shown by this dotted line. And what's remarkable is that the superconducting dome occurs right here in this minimum of resistivity. Okay? And just to set a scale for what we're seeing in terms of this kind of milliohm centimeter scale resistivity, this dotted line, or sorry, this gray dashed line here, is the resistivity you would get for a quantum, a resistance quantum per nickel O2 plane. So this is not to say that we know that it's so strongly two-dimensional. We don't actually right now have any direct experimental information of the C-axis conductivity. But just to set the scale, it's quite suggestive that right here is the only regime where, in the simplified thinking, we were dipping into the regime of having coherent transport. So to give you a scale, KFL in 2D units here is of order 4 or 5, right? So barely coherent transport. And perhaps it's not a coincidence that only in this kind of maximum conductivity regime is where we have precisely the observation of superconductivity. But either side of this is rather distinct, okay? And yeah, I'll come back to some thoughts on that, mostly from other groups. So one of the things that we, of course, wanted to ask ourselves is, from a chemical formula point of view, we think we're doing whole doping, but what does the Hall coefficient tell us? And this is the doping dependence of the normal state Hall coefficient. There's quite a bit of data here, but again, there's some simple things that we can deduce. So here's the undoped neodymium nickelate. Okay. So the Hall coefficient is negative, and if I naively attribute this to a single band free electron-like picture, the carrier density we would get is something like 8%, or 0.08 electrons per formula unit. On the other hand, as we then think we're doing whole doping, the Hall coefficient remains negative but gets smaller and smaller. So this is highly inconsistent with this picture. This would be as if we're making it a higher and higher electron density. The second thing that is immediately apparent, that both as a function of doping or as a function of temperature, we have this very smooth crossing of zero in terms of the sign of the Hall coefficient. So just to remind you, this is very different from, okay, so let's take graphene, for example. As I gate from electron doping to hole doping, the Hall coefficient itself is diverging on either side of that, right? And so in fact, the simplest picture one can have for this kind of continuous zero crossings and qualitative description is for a multi-band scenario, namely a case where I have both electron and hole pockets in the system. So I'll turn back to theoretical discussions in a moment, but if I have a system where I have, for example, this kind of configuration, that even though we're doing hole doping, because we have this landscape of both hole-like Fermi pockets and electron-like Fermi pockets, we can nicely, at least that would be one self-consistent explanation of this data. So similarly to the resistivity here, if we look at a low temperature normal state slice of the hole coefficient, we can see that there is this zero crossing. And again, it's suggestively close to in the immediate vicinity of the superconducting dome. So these 4 samples here are those that are superconducting. Now we would love to be able to try to get some more estimated numbers out of this. Many of you in the audience are quite familiar, I'm sure, with this kind of 2-band fit. Our problem right now is that we are under constrained, namely our Hall coefficient is linear up to, let's say, at least 14 Tesla scale. The magnetoresistance is very small, and on top of that, it's negative. So it's not simply interpretable in a 2-band picture. So these are a little bit limitations before hopefully someday somebody can access the Fermi surface directly by ARPAS or something. This is our current understanding. And again, this cartoon is pretty consistent and was certainly motivated by the results of band structure calculations. And so again, going back to this paper by Lee and Pickett for lanthanum, neodymium is basically the same, by the way, nickelate, you have these large hole-like pockets from the x² - y² states. And from the hybridization with the 5D states, you have these 2 little electron pockets. Okay, so in a qualitative sense, this is quite consistent with at least what we see by Hall coefficient measurements. I should also say that in this early work, they tried to investigate computationally what happens as you start to increase the electron interaction. So this is LDA plus U type of calculations. And I just qualitatively wanted to trace through one thing, which is that this is the uncorrelated band structure. And as they increase these correlations on the nickel 3D site, what you can see here is that the x² - y² states, this cuprate-like hole band, splits to an upper and lower Hubbard band, as you might expect. But this additional feature of having these small electron pockets is quite qualitatively different, namely that you have also then a splitting of these z²-like symmetry states, but you end up pinned in terms of having a Fermi surface, even up to very high interaction strengths at the Fermi surface. So that in some sense gives you a natural explanation of why we don't have a good insulator. Various people, Fucheng Zhang, for example, have used the term of a self-dope mod insulator, that because of these peculiarities of the band structure, that there is internal kind of charge transfer and partial doping, or having partially occupied states. Of course, we don't yet know in detail where we are in terms of real parameters relevant for experiments. My theory colleagues tell me we're probably living in this range of U of 5 or 6 or something like this. But clearly much more work needs to be done spectroscopically to try to narrow this down. But yeah, let me just try to take a moment to discuss what people are thinking about. Now, there are many, many papers on coming out on the system. The theory community is working very fast, and I have certainly not the expertise and also time limitations, but let me just sketch out some of the early themes that have come out. So there's a clear convergence of the LDA limit of band structure. First, I'm just quoting kind of first papers that came out on these various topics. On the other hand, there's a fair amount of heterogeneity as people deal with the difficulties, as you know, of trying to handle strong interactions and doping in electronic structure calculations. So to some degree, the details of how that is approximated matter in detail. But certainly there's kind of a universal agreement of the starting band structure that we're talking about. The second statement would be kind of thinking about electronic superconducting instability, so random phase approximation or TJ models, kind of all lead to dominant dx squared minus y squared pairing. That even though we have these small electron pockets here, essentially superconductivity is governed by something that in these theoretical approximations looks very cuprate-like. I forgot to mention before, but I should also say that the resistive upturn, sorry, let me go to a clean version of this. That a number of people, and like I said, Hwang was one of the early ones to point this out, could be interpreted as kind of a Kondo effect, that you're seeing a Kondo upturn in the system. And again, there is some sensibility to this notion in the sense that the electronic landscape is one of having a narrow upper Hubbard band in the nickel site across a broad, kind of broad bandwidth rare earth or lanthanum 5D states. It should also be said, I mean, at least I'm on the experimental side, it should also be said that the fidelity with which we know precisely the stoichiometry should be, you know, taken with a grain of salt. And so we also have to consider the possibility that the detailed, you know, did we properly and fully reduce the oxygen? Are there interstitial hydrogens? We're working to try to narrow down these numbers, but there's certainly some uncertainty there. So you should keep that in your mind. Two other things that I can just mention is that there's an interesting possibility that's been raised by these two papers early on and others subsequently, that actually that we might have the proximity or the instability to actually make spin equals 1 whole states, okay? And what that means is, you know, sorry, it's a bit small here, but we start with these 9D electron configurations. As we know from the cuprate language that we're taking out an oxygen hole-like state. But what happens if we're actually have a non-trivial Hund's coupling and we're going to a high spin configuration? So that has a number of interesting consequences. I would certainly also mention that indeed that's what's found in the two-dimensional layered nickelate version of D8 configuration. So namely lanthanum 2 nickel 04. So this is very much the same structure as the 214 cuprates. In this system, when you dope, whole dope, let's say strontium into the lanthanum site, indeed what you find is the high spin configuration. So it's not completely clear where we are. This is certainly something we're interested in pursuing spectroscopically or thinking about. But certainly both of these papers estimate that we're actually close to this boundary between the high spin and low spin configuration. And finally, there's an interesting additional problem in that majority of the early electronic structure calculations have essentially dealt with all of the 4F states in the core, right? It's quite computationally expensive to deal with, and is in most cases fairly electronically inert. However, it is obviously a possibility. Namely, is there the possibility that you have direct hybridization of the neodymium 4F states with the chemical potential? So this is just my cheeky way of putting this. Is this a Kondo-Kondo problem? And at least one early paper on this was also coming from Warren Pickett on this issue. So we don't really know the exact answer to this yet, but at least one partial comment we can give is that we've recently published the observation of superconductivity in praseodymium strontium nickel O2. Superconducting properties are rather similar actually to the neodymium case. And I won't go into them in detail, but the main point is that going from neodymium to praseodymium, one expects in general that the 4F level alignments are going to be moving around non-trivially. And so it'd be rather extremely unexpected to have direct hybridization or coincidental lineup in both of these cases. So in that regard, we tentatively would suggest that this is not crucial to the occurrence of superconductivity, but certainly the question of the 4F moment and how it may or may not couple to the system is an open question. So yeah, so let me also mention that recently some important papers have come out on ConMat. Independent groups have experimentally observed a very related phenomenon. The first paper that I'm aware of is this, what is this, in April from a group at the University of Singapore. There's quite a bit of work actually that they did. And basically what they did in this first paper was the entire superconducting dome, just as I presented to you. Hall coefficient, many of the details are quite similar. I didn't mention it before. I don't know what the significance is yet, but they also see this strange dip in the superconducting dome. And what is actually amazing to me is despite the tremendous difficulties we have in stabilizing these materials, these two papers are qualitatively quite similar. So at most, there's something like a 2% shift in doping of the relative position of the dome. To me, this is kind of well within experimental, let's say, noise. One distinction is that the resistivity in the Hall coefficient scales by about a factor of 5. And at least in my I can't speak for them, but certainly if they had this kind of two-phase segregation, at least it'd be self-consistent with what we had previously observed. But modulo these slight differences, it's remarkably self-similar. And also they did a nice plot here of the sign change in the Hall coefficient as a function of temperature, which they correlate with this dip in the superconducting dome. More recently, there's been another group at, what is this, Nanjing, that also has observed superconductivity. I think these were pulse laser deposition samples. I think these are MBE, I presume, films. And so now, you know, again, important that independent groups are also seeing similar things, and hopefully there'll be much more to come on the experimental side. Right now, experiments have been slow compared to the theory side of this world. So I think I'm on pace. I think it's possible I finished slightly early, but given that it's Friday evening in Europe, I don't think anybody will complain too hard. But I wanted to end with some fairly recent things that we've been working on, thinking about the upper critical field anisotropy, a little bit trying to now delve into the physics of this, of the superconductivity of the system. I should first thank that this benefited a lot from the expertise and insights of Mac Beasley. And in some sense, this is a picture of one of the samples that I'm going to show you. And you know, the idea is that we've been working harder and harder and harder to try to clean up the materials. So I think this is both representative, but also kind of state of the art. And for some reason, a little bit unknown to me, is at least within what we've measured, this composition seems to have the nicest crystallinity. You can see here that it's fairly coherent, but it does still have extended defects, right? So this is kind of where we're at materials-wise. But since this is kind of the cleanest thing that we can reproducibly synthesize, let's use this as a focus of studying the upper critical field. So the experiments are simple. We're just looking at the resistive transition in the magnetic field. I can go into more details if you like later in the discussion, but for what I'll show you, we'll just use a 50% of the normal state as a criterion or proxy for the upper critical field in the system. So both in the perpendicular and parallel direction. Okay, so let's first look at HC2 parallel. So this is putting the magnetic field in the plane of the film and in the critical regime near TC. And what I'm showing you here, it has a very nice square root of reduced temperature dependence. Okay, and so yeah, Jean-Marc, Andrea, many of you that I was chatting with at the beginning, you know, at least in my limited experience, you see this, you say, I know what this is. This is a thickness limited superconductor, as you see in LAOSTO, or in our lab, we've also been playing with geometrically confined delta doped STO. So that's a scenario first discussed by Michael Tinkham, a case where you take, let's say, a three-dimensional superconductor, you make it very, very skinny such you quench orbital motion for the in-plane direction, and it has, for the linearized Ginzburg-Landau form, a very simple functional form that gives you this characteristic square root of reduced temperature. And commensurate with that geometry, then what this, the two length scales involved are the in-plane coherence length and the, in bulk, this would have been the out-of-plane coherence length, but in this case, it's the thickness cutoff of your geometry. And so what we see is actually, although there's a beautiful square root temperature dependence, the numbers are terribly off, you know, not a few percent, but we're talking about factors of 3 or more in terms of the known crystal thickness that we can measure by, for example, X-ray scattering measurements, or in this case, say by just TM, direct inspection. You can see here that the thickness we derive from this Tinkham-like fit is horribly off. And it's all even going in the wrong direction. That namely, that if I went from this thick to thin, I would expect HC to go up. But actually, asymptotically approaching TC, they all look the same. Okay. So this is very puzzling, and then it basically experimentally shows us that we are not actually thickness limited. We don't have that much of a thickness variation that we can access given the stability constraints that I told you about earlier. But certainly we could easily see these variations in, for example, other geometrically combined superconductors. Doesn't make any sense. And the final comment I could make is for those with expertise, you know, spin-orbit coupling can also change this simple interpretation, but that constraint, sorry about this, is going in the wrong direction, actually. That should give you a thickness underestimate and not the other way around. Sorry, let me just let it ring. Hopefully that will go away. So given that it doesn't seem to matter what the thickness of the actual sample is, and yet we see this nice square root dependence, an alternative explanation is that this is intrinsically Pauli-limited in the in-plane direction. These are actually old ideas. Namely, I'm now plotting this critical regime for the in-plane upper critical field scaled as HC2 squared here. And then in this case, rather than being geometrically confined, that you're intrinsically limited by the Zeeman scale. And then the interesting consequence of that is that the scale of this HC2 variation, this would also give you a square root of T, can give you a measure of the effective magnetic moment associated with the normal state electrons, right? So it's this competition between pairing versus Zeeman scale here. And we get an enhancement here, actually. This is the number we get from this t-squared fit. Okay, I'll come back to this in a moment. Now, in the out-of-plane direction, as I had briefly showed you at the introductory part of this discussion, we see a nice kind of conventional upper critical field, so a linear variation. And so this indeed is conventionally associated with orbital depairing. And again, this gives you a coherence length of something like 3.5, 4 nanometers typically. Okay. But now let's stay in this perpendicular field direction and look now more broadly as temperature. And this is the raw data here. This is HC2, again, in the perpendicular direction. Here's the linear regime I just emphasized to you. But as we go in temperature, it has this rather strange variation. And what we conclude by kind of taking this classic analysis of thinking about pair breaking is that we're also rapidly polylimited even in the out-of-plane direction. And so, for example, if we take a simple fit to just an orbitally limited upper critical field, we would have this red curve. But if we take this kind of consideration of pair breaking by spin orbit scattering into account, we would get this green curve. And the point of this qualitatively is to say that even fairly close to TC, we rapidly cross over to be limited by the paramagnetic response in this as well. So there's quite a bit to unpack here, but let me just give you the experimental survey of where of what we see. This is down to a leaky helium-3 system, so about 0.5 Kelvin. And so here's the raw data in circles. Okay, so this is in the perpendicular orientation. As I mentioned, it's linear approaching TC. We extract a coherence length of about 4 nanometers in this case. This is what I just described to you in the previous slide. And now we're taking so-called WHH fit. So this is an extended theory taking both orbital and paramagnetic effects into account into the full theory. And this is a second order fit to this WHH fit. Okay. Now, this is the in-plane direction. Again, we put the magnetic field in the plane. This is the square root that I told you about. As I previously discussed in some detail, it doesn't scale with the geometry, nor does it give you a sensible number for the thickness. And then it varies in this rather unusual way. So let me tell you what we think we can say confidently and then end with some open questions. The first thing that's rather remarkable about this layered superconductor is that this is now just overlaying the two directions side by side. It's remarkably isotropic. Right? So think about what you know from the cuprates, or if you're less familiar, also strontium ruthenate, or cobalt oxide, the sodium water intercalated cobalt oxide. These are all very strongly anisotropic. Okay? In this case, at least experimentally, we certainly see that it's quite isotropic. And I think the simple understanding that immediately pops out of our analysis is that we're dominated by the polylimited. So it's the spin response of the system that is largely isotropic that sets the scale for the upper critical field. And as I told you, that if you take this square root as a measure of the susceptibility of the normal state, then this would give you the scale of the poly limit associated with this enhanced susceptibility. And it's quite reasonable in the sense that the basic HC2 fit extrapolates to that vicinity. It's a little bit higher because of spin orbit coupling in the system, but nevertheless, this sets the scale. And of course, because we don't observe a region that is simply orbitally limited, we can only give, say, a bound on the c-axis coherence length, unfortunately. We give, I can go into more details later, but about a nanometer bound for that direction. So that's the main message, which we have the shockingly isotropic superconductor, and we believe that the poly limit is really governing that scale. What is obviously an intriguing feature that at present we don't feel like we can definitively assign is this low temperature upturn that you see in both directions. Okay. So I can just say in words that we've been thinking about various possibilities. One of them being, let me list a few then. One is that we can unconstrain the WHH fit to be to allow for a first order crossover. And so this might be associated with a second order to first order crossover. You could think in terms of multi-band superconductivity, perhaps. Qualitatively, it doesn't really seem likely, but the possibility of having a second band condensing. Of course, for many of you, you look at this, and if I didn't tell you anything else, this almost looks like the textbook theoretical picture or model of what the FFLO state might look like. And so despite that tantalizing similarity, we don't feel like we're, at least within our understanding, in a regime where that is very plausible, because our transport numbers that I briefly mentioned to you and analysis suggests that we're quite in the dirty limit as far as superconductivity is concerned. So kind of finite Q pairing states and these sorts of more exotic possibilities are generally associated with clean limit superconductivity. So it's not a natural explanation. So clearly a lot to be done to understand the nature of the low temperature upturn. One of the things that I don't think there's consensus, by the way, among my collaborators here, but at least that I keep getting excited about is that if I extrapolate to the low temperature limit, this upturn looks like it's going to hit in the vicinity of the bare Pauli scale. Namely, if you forget about the susceptibility enhancement, but just go to kind of a free electron value, that seems to be not far from where we might be headed at low temperature. So this becomes a bit of an experiment we can't do in our lab because we need to go down to Dilfridge temperatures and higher magnetic fields, but this is clearly an interesting regime to ask, which is what is the ground state at high magnetic field of this superconducting phase? So clearly much to be done. So let me wrap up here. And despite talking for so long, the summary is that this is very early days. So we have more questions than we have answers. But let me simply say a few things, which is that we clearly, and others have observed, a superconducting dome, but an open question is proximate to what? In the nicketides and the cuprates and heavy fermions and these sorts of systems, there's a proximate magnetic ordered phase, or if we want to get exotic in strontium titanate, proximate ferroelectricity, but we don't have an ordered phase that we know that we're proximate to. So that's an interesting open question. The second point I want to emphasize that despite the similarities of the superconducting dome structure, that the normal state is quite distinct from the cuprates. And it may be the case in very fundamentally important ways. What I'd like to emphasize here is that again, I go back to this picture, in the cuprates, the notion is that this charge reservoir layer is pretty inert, meaning you can dope, let's say, lanthanum and strontium there, but the charges are transferred to the copper oxide plane. That no states near the chemical potential arise from these levels, okay, or from these atoms. And so essentially this is a source of disorder, remote ionized impurity scattering, these sorts of things, but otherwise electronically inert. What is pretty clear from all of the theoretical work in this field is that the rare earth states in our charge reservoir layer have a much more active role, namely that they are hybridized such that they contribute band states in the vicinity of the chemical potential. So that's quite qualitatively distinct. But then we also should consider that the doping of these states is again a complicated theoretical question, difficult to address. Namely that if I'm worrying about band states arising from, let's say, the neodymium in this layer, as we non-trivially substitutionally dope with strontium, the overdope side of our dome, if you want to call it that, is 25% substitutional doping. This is very heavy disorder. This becomes more like a random alloy type of situation, and how we think about that I think is an open conceptual question, but certainly qualitatively one of the things that we're worrying about in terms of why we don't see a good metallic overdoped regime. And finally, I showed you a rather surprised or unexpected for us observation that the upper critical field is quite isotropic and seems to be governed by a poly-limited scale in terms of HC2. And so, again, as far as I am aware, I don't know of any oxide systems where that is the case. The few cases I'm aware of are like heavy fermions, and so that seems also rather unusual and much more to be studied, especially with respect to this low temperature upturn. The final thing is quite speculative, but nevertheless I think relevant, is that if you think about the cuprates or the pnictides and so forth, Mother Nature gives us a huge family of interesting structural motifs and compounds to play with. And I would say that the nickelates as well, in the sense that I think this was early 90s, people first started to discuss and report that if you start, rather than with the perovskite phase, like everything that I talked about, but start with different layered Ruddleston-Popper series samples and then do this oxygen deintercalation reaction, you can make a whole family of compounds with various kind of multi-layer infinite plane structures, so bilayer, trilayer structures. Okay. And in fact, quite a bit of work has been going on in this community as well. And so let me just show you a few pictures from a tri-layer version of this. So this has 3 infinite layer planes, let's say a spacer layer, and then so forth and so on. It's a rather interesting system. Maybe I won't discuss the details, but the tri-layer version has been investigated heavily by John Mitchell and his collaborators at Argonne. Bilayer version, there's been a fair amount of work by Marta Greenblatt at Rutgers. Is quite an interesting story. The brief statement is that almost every ground state other than superconductivity has been observed, namely insulating and metallic ground states. And they're very susceptible to density wave instabilities, both spin and charge sector. If you naively take kind of the electron count given by the crystal structure, these would generally be overdoping, right? So it's kind of 1 over the number of layers. So this would be something like whole doping to the level of 1/3 or 1/2 in the bilayer case. So at least it's possible that the reason superconductivity hasn't been observed is the chemical or the whole doping level is too high. I don't know if it's feasible, but one could imagine asking whether you can then do further chemical substitution on the rare earth site in order to explore the doping phase diagram of these, say, bilayer and tri-layer infinite layer polymorphs as well. So just a question and a speculation, but certainly an exciting one to think about going forward. So yeah, I think the summary is, I hope it was interesting for you. I tried to survey what little we know so far. There are many more things to do than we've done as a community, and I wanted to thank you for your attention and thank the organizers again for this opportunity.
Thank you, Harold. And now this is open for discussion. So if people have questions, I would invite them to unmute the microphone and ask Harold directly.
I did on my side.
Actually, I have 2 questions, but since I was the moderator, I will wait.
Okay.
Mark, do you want me to start with a question?
Please. Yeah, sure. Go ahead.
Thanks, Harold, for the beautiful presentation and beautiful results.
Thank you.
One question regarding the what you showed at the end is fascinating critical field measurements.
Uh-huh.
The question is, I think on one of your slides, you were careful in mentioning we do not or we neglect flux flow and things which could affect the critical field measurement. This is in fact my question, because you extract now parallel and perpendicular critical fields. Are the results affected by the criterion you're using to define TC?
Yeah, very good. Okay, yeah, I'm talking to an expert. So let me just say roughly, I can try to dig out more details, but let me just show you, for example, sorry, this is a bit busy. So this is the kind of thing that we were worrying about. One is that in the vicinity of TC, obviously we can worry about the onset of TC, we can worry about superconducting fluctuations. So these dotted lines are 2D Aslamazov-Larkin fits. Now I should say that I think our transitions are relatively broad. And so we can worry about intrinsic quantum fluctuations as well as just disorder broadening. So that's one issue about a very high transition temperature definition. The second thing we see is, do I put it here? We see what looks, just following like actually classic work by Tom Palstra and these sorts of people on vortex motion and flux flow regime. We again kind of see very similar things to what is seen in cuprates in terms of having an activated dissipative transport associated with vortex motion and these sorts of business. So to get back then to your question, at least phenomenologically, I could say the following. So this is percent here means, for example, 1% resistive transition, so very close to the normal state. 50% or 90%. And then this line here is, for example, using these Aslamazov-Larkin fits or the threshold for where we see vortex-based dissipation. So to make a long story short, I forget the exact numbers, but somewhere between 20% and 80%, if my memory serves, of the resistive transition, our analysis is qualitatively robust, meaning, some of the numbers change a little bit, but what we see is the same. But then outside of these thresholds, so above 80, 85% or so, or below 20, 25%, we feel that we're clearly like going into a different regime. And one of the ways you can obviously see this is in the perpendicular direction, where we have, what we're interpreting as orbital depairing. As we go to higher and higher threshold criterion, we're changing even the functional form. Right? So that's kind of what we know at present to address your comment. Yeah.
Mm-hmm. Thank you, Harold. Just one more thing. I mean, I was trying to remember, and I did Google, but I couldn't find the answer. What is the anisotropy of the infinite layer cuprates? Do you know?
Yeah, I should know, shouldn't I? It's pretty big. So just to, okay, I say to remind you, I was just recently learning. So one of the motivations from an applications point of view of infinite layer cuprates was the hope from a technology point of view of having an isotropic upper critical field. And it never really quite worked. I think the anisotropy was still a factor of 5 or more. So namely, it was something like half a nanometer, 0.4 or 0.5 nanometers out of plane and a few in plane. So that's so what was the cuprate case. Yeah.
So quite different. Okay, thank you. Thank you, Harold. Go ahead, Jennifer.
Okay. There is a question by Yorick, so please unmute.
Hi, everyone. This is Yorick from Twente. Thanks, Harold, for the nice talk. My question concerns the synthesis of the product. One of your very early slides, you indicated that the strontium-doped neodymium nickelate is under quite some high tensile strain,
Yes.
and 2% or so. So that makes me wonder, did you explore different substrates like a dysprosium scandate to stretch the system even further, or LSAT or NGO?
Yeah, so we're doing slowly. So let me just make sure I was clear. So at least, you know, if we take the undoped case, neodymium nickel 02 or lanthanum nickel 02, that there's already a fair amount of prior bulk work. And what I mean to say is that the perovskite, the O3 versus the O2 phase requires an A-axis lattice expansion of about 3%. And so if we've grown and played with this in film form, we have this interesting dilemma. Okay, I won't try to dig around quickly, but what we are finding, in fact, there was a nice paper recently came out in Nature Communications by Beatrice Nohida, where they were only working on the perovskite phase, but they were varying different perovskite nickelates on various substrates. And what we think is going on is that, let's find a nice TM picture. What we think is going on is that, so in order to accommodate the strain of our particular substrate, this is under a fairly high tensile strain, there's an intrinsic instability to make vertical Rudolphson-Popper-like fault intergrowths. This is kind of the way the system is trying to deal with this unhappy situation. So there was at least the first work I'm aware of in the field was from TEM point of view was in this paper by Beatrice. We see very similar things. So what we worry about or suspect that's a little bit discussed in this paper is that whatever cation configuration we have, our low temperature reduction doesn't do much to it. So whatever the perfection or imperfection in the perovskite phase is basically the same mirrored into the infinite layer phase. So the dilemma though is, actually maybe I have a nice story here. We haven't been profoundly productive lately with all the stop-starting business, but maybe there's also one thing I could tell you. So then you can say to me, all right, then the answer is clear. Get a better substrate where this, you know, our thinking so far was let's try to get a substrate where we match as perfectly as possible the end product. But you could do the opposite thing. You could make this guy happy. But at least qualitatively, one of the things you may have to worry about, and again, this is a work from Professor Shimakawa and colleagues, lanthanum nickelate is a bit closer to that regime. And what they find is that when they reduce their films, it goes from this to this to this, but actually the final stage is that the planes stand up perpendicular to the interface. So qualitatively, I understand this to be all driven by the kind of energetics of accommodating that strain state. And so, for example, here's another dilemma. It's not easy to do, but you know, there are a few groups that can do high pressure bulk single crystal synthesis. And I think the dilemma there is now, why don't you reduce that? There's nothing to break the degeneracy. I can pull out this plane, this plane, this plane. And so you kind of make a little bit of a, at best, a polycrystalline kind of mess. And so I think that's the trade-off for the thin film case. We've done a little bit of work on, let's say, proximate substrates like LSAT seems to work okay, but big swings in lattice parameters we haven't really fully explored yet. So I don't have an experimentalist statement of what happens, but I think these are the trade-offs you need to consider in that possibility.
Thank you.
Sure.
Okay, so there is a question from Marius, who is part of the Jean-Marc gathering.
Okay. Yeah, the question was based on your previous answer, actually. In the study by Professor Shimakawa, where they showed that the infinite layer planes change orientation. I guess, I'm not sure, have you seen anything similar for the neodymium nickelate? I guess that wouldn't actually stop. So if you had the infinite layer planes perpendicular, you would have quite an interesting structure. So is it something that you've seen?
Absolutely. So I think you're exactly right that if this is controllable, there's a very interesting thing, opportunity there. I'm not sure that we can be comprehensively exact here, but at least so we haven't ever seen this reorientation transition in the neodymium nickelate. So namely, we basically make the infinite layer phase, and if we just go to longer and longer or higher temperature reduction reactions, we go from that to decomposition. So my cartoon understanding is that in the neodymium infinite layer phase, we're pretty well matched and a little bit tensile, right? So that if strain's driving this reorientation transition, that won't be the case for neodymium. Whereas for lanthanum, for the infinite layer phase, we're a bit compressive. So that could be an explanation of why it reorients. So, so we haven't seen that reorientation in neodymium, although we have reproduced and seen that for the lanthanum case. So for our present purposes, what makes that nice is that kind of, we're just watching the, you know, in everyday life, we're just watching the X-ray diffraction, and you can see it getting pulled further and further out and stay sharp. And if we go too far, then we just see this decompose. And so that kind of gives us a nice endpoint to go to. Whereas with the lanthanum case, you have to be a little bit fooling around to try to get there, but before you stand up in what we've done so far. Yeah.
Okay, thank you.
Sure.
Other questions? Well, okay, I'll shoot since I had two. You can measure in a magnetic field, which is either applied parallel or perpendicular to the film. And so going back to the comment that you were making on the light upturn in the resistivity at low temperature, and you were sort of exploring scenarios. If it were Kondo, you could tell in some sense by the magnetoresistance, it would be more or less isotropic.
Yeah. So I don't think I have here the full anisotropy. Sorry, this is a bit busy, but let me just give you, the bottom line statement is the normal state magnetoresistance is puny. It's very small. So this is, let's say, the undoped compound, X equals 0. And this is, say, the 10 Kelvin magnetoresistance. You can see that this is of order of percent at 10 Tesla. Okay. Now, of course, if you take the Kondo scale to be whatever, 80 Kelvin or something, maybe we need a lot of field. But overall, the magnetoresistance is small, and I believe outside of a regime of picking up superconducting fluctuations, fairly isotropic, but we haven't, I have to be careful actually, especially if we're recorded. I think that's true, but I'm not sure. Yeah. But basically the magnetoresistance has been pretty boring to study in the normal state to some degree, because not much happens.
Okay. And so the second question I had was, in some sense, just like in LAOSTO, if you count the valence naively, then you'd conclude that the interface with STO is polar. I mean, in your opinion, is this playing any role at all or not?
Okay, so certainly based on my past, I must believe that that's important. So let me just say for, what's a good picture? So what Mark is pointing out is that if I do a naive count, this will be actually +3, -3 layers. So I have the same electrostatic problem, or actually even a worse one with the interface with strontium titanate. So what's going on? I should say that there's at least a few papers, electronic structure calculations worrying about this in detail. I would say two things is my best answer right now. One is I feel reasonably confident that it has to be a bulk effect across the film, in the sense that the critical current densities, as I say, we're now getting up towards 400.
Hello? Hello? Is anyone hearing me? I cannot, something froze.